This here is the choke point, the Chicago Sanitary and Ship Canal. The fish would have to come through here, which is why this water is electrified. The US Army Corps of Engineers have put a giant electric fence underwater.
If you ever feel like going fishing near Chicago, think again. This might look like an ordinary stretch of water, but there's something very unusual going on here. You won't find fish swimming around, or anything else really. No birds dipping in for a snack, no signs of aquatic life. And if someone accidentally falls in, they're on their own. Even lifeguards won't come to the rescue, not because they're unwilling, but because jumping in would likely get them killed. What makes this stretch of water so dangerous? In a word, electricity. Roughly 25 miles southwest of downtown Chicago lies a small town called Romeoville. Here, the Chicago Sanitary and Ship Canal has been turned into one of the strangest waterways in the United States. Deep beneath its murky surface lies a hidden defense system, rows of electrodes installed on the canal floor, designed and built by the U.S. Army Corps of Engineers. These electrodes deliver powerful pulses of 2.3 volts every 2.5 milliseconds. The result? A deadly electric field that stops nearly everything in its tracks. So, why would the U.S. government electrify a public waterway? The answer lies in an unexpected threat: a fish. Specifically, the Asian carp. To understand why this fish has triggered such an extreme response, we need to look back a few decades. Asian carp were originally introduced into the United States over 50 years ago to control algae in wastewater treatment plants and aquaculture ponds. But they didn't stay where they were supposed to. Floods and human error helped them escape into major river systems, and once they were in, they took over. Today, Asian carp dominate entire waterways across the Midwest. In parts of the Illinois River, for example, they make up more than 75% of the total biomass. In other words, if you scooped up all the living material in a given stretch of water, most of it would be carp. These fish are incredibly disruptive. They eat everything native fish eat, outcompeting them for food and space. They stir up sediment from the riverbed, making clear water murky, which affects plant growth and aquatic ecosystems. And they're not just an ecological nuisance, they're a physical danger too. You've probably seen the videos, dozens, sometimes hundreds of carp leaping into the air as boats pass by. It might look like a nature documentary on fast forward, but it's dangerous. These fish can weigh over 30 pounds. Getting hit in the head by one isn't just painful, it could knock you out or even break bones. Now imagine what would happen if these fish made their way into the Great Lakes, a region that holds 21% of the world's surface fresh water, supports over 150 native fish species, and sustains a multi-billion-dollar commercial and recreational fishing industry. That's why the U.S. government built 3 electric barriers along the Romeoville stretch of the canal. The first began operating in 2002, followed by a second in 2009, and a third in 2011. Each consists of steel electrodes embedded in the canal floor, connected to a building nearby, where the entire system is monitored and controlled. These barriers generate an electric field that discourages or incapacitates any fish trying to swim through. But they're not foolproof. For one thing, the system doesn't work 24/7 without interruptions. Maintenance or malfunctions sometimes require the electricity to be turned off. And while these shutdowns are temporary, they're long enough for opportunistic carp or any invasive species to potentially slip through. In 2009, fearing a possible breach, officials poisoned nearly a 6-mile stretch of the canal beyond the barriers. The result? Thousands of dead fish, and only one confirmed Asian carp. It was a relief at the time, but soon after, DNA testing began revealing troubling signs. Traces of Asian carp genetic material north of the barriers, closer and closer to Lake Michigan. Then came the bombshell. In 2022, a live Asian carp was captured just 7 miles from Lake Michigan. It had somehow made it past not just the electric barriers, but also an unfinished secondary line of defense, the Brandon Road Interbasin Project, a massive infrastructure effort designed to be the final buffer before the Great Lakes. The discovery triggered alarm bells across multiple states. Illinois and Michigan quickly funneled $14 million in emergency funds to speed up construction. The total cost of the Brandon Road project is expected to exceed $1.2 billion, with completion targeted for 2029. So, what makes this new system different? Rather than relying solely on electricity, the Brandon Road Interbasin Project introduces a multi-layered defense strategy that combines technology, physics, and fish psychology. The first line of defense is a bubble curtain, a continuous stream of bubbles that creates water movement and noise. This is designed to push away fish that might be trying to ride between the tight gaps of barges, which are often pushed down the canal in long chains. Next comes a sound barrier. Underwater speakers emit noises at specific frequencies that are highly unpleasant to carp. Research shows that more than 99.5% of carp turn away when exposed to these sounds. But if any manage to get past that, there's another bubble curtain. Think of it as reinforcement. Following that, carp must swim through a featureless concrete channel, with no rocks or structures to rest behind, and no food to be found. The current becomes even harder to fight. The message to the fish is clear. Go back. Still stubborn, the final line is another electrified zone, stronger than the previous ones. This one doesn't just scare, it stuns. Once incapacitated, the fish is swept away by the current, pushed back through the very gauntlet it just passed. And if a carp miraculously survives all of this, there's a sluice gate at the end that creates a powerful backflow, flushing any remaining intruders back downstream. Until this project is fully operational in 2029, the current electric barriers at Romeoville remain the primary defense. But even they come with risks. Because of the electrification, no one is allowed to swim or rescue anyone who falls in. Signs and fences warn people to stay away, but accidents can happen. If someone falls into the canal within the electrified section, emergency services won't attempt to rescue until the person drifts at least 450 feet downstream, beyond the danger zone. It's brutal, but it's policy. The danger was made clear years ago when a barge crew accidentally created a spark by mooring with a metal rope. Thankfully, there were no explosive materials aboard. Had there been, the result could have been catastrophic. But despite the grim nature of this waterway, some people have found a more hands-on way to fight the carp invasion by catching them. Every year, particularly along the Illinois River, tournaments are held to capture as many Asian carp as possible, not with fishing rods, but with nets. During these events, boaters zoom along the river and thousands of carp leap into the air. It's chaotic, dangerous, and weirdly exhilarating. Helmets are strongly recommended. In 2018, one such tournament attracted competitors from around the world, and more than 5,300 carp were caught in a single day. It's fun, but also useful. Every fish caught means one less threat to the Great Lakes. Outside of tournaments, there's been a major push to remove carp commercially. Between 2021 and 2022, Kentucky alone removed over 6 million pounds of invasive carp, and since 2019, more than 10 million pounds have been pulled from the Illinois River. Some of the newer capture methods are remarkably efficient. In one test in Kentucky, a specially designed sound and light trap helped collect 27,000 pounds of carp in just 4 hours, with minimal bycatch. Another method involves mobile electric fishing boats. These boats create localized electric fields that temporarily paralyze carp. The stunned fish float to the surface, where they're collected for tagging, study, or disposal. This method is particularly helpful for scientists who are still learning about carp behavior and biology. Which brings us to a surprising twist. Asian carp are edible. In fact, the Illinois Department of Natural Resources has launched marketing campaigns to rebrand and promote them as a tasty, sustainable food option. It's too early to tell if the public will embrace carp as the next big culinary trend, but early sales have already exceeded expectations. Meanwhile, scientists are working on longer-term solutions. One team from the Minnesota Aquatic Invasive Species Research Center is developing a genetic control system. Their idea: release genetically modified male carp that cannot reproduce, slowly reducing the population over time. It's a war on many fronts: electric barriers, bubble walls, sound deterrents, fishing tournaments, marketing campaigns, and genetic engineering. But it all started with a simple idea: stop the carp before they reach the Great Lakes. And for now, the electrified waters of Romeoville remain one of America's most unusual and high-voltage battlefields. Look closely at this small town, Maxwell, California. With a population of just around 1,000 people, it's a quiet, unassuming place nestled in the northern part of the state. There's not much that makes it stand out, except for one thing. Soon, nearly 475 billion gallons of water will be stored in a nearby valley, thanks to a new infrastructure project with a jaw-dropping price tag of $4 billion. At first glance, that might sound contradictory. California is notorious for its water shortages. In many parts of the state, residents are used to saving water year after year, cutting back on everything from showers to lawn irrigation. Farmers, who make up a large share of the state's water consumers, are under constant pressure to conserve every drop for their crops. With such a strong emphasis on conservation and such tight regulations on water usage, how does building a massive new reservoir, one that releases a huge volume of water into a drought-prone region? Surprisingly, this is California's strategy to fight back against its increasingly unpredictable water future. Let's dig into the problem first. California's geography is a major challenge when it comes to water availability. Large portions of the state are made up of deserts. Take the Mojave Desert, for example. It covers more than 13,000 square miles, but receives only 2 to 6 inches of rain per year. With temperatures regularly soaring over 100 degrees Fahrenheit, most of that rain evaporates before it can be of any use. Then there's the Colorado Desert, covering another 10,800 square miles, where similar conditions prevail: hot, dry, and unforgiving. And don't forget about the sprawling Great Basin Desert, which extends into eastern California. It receives just 6 to 12 inches of rain annually, making the landscape inhospitable to large-scale water storage without major engineering. California's natural environment simply doesn't support stable, abundant water supplies. But the situation gets even worse when you factor in the drought cycles. In July 2021, for example, Governor Gavin Newsom urged residents to reduce water usage by 15%. That wasn't new. In 2015, amid another severe drought, then Governor Jerry Brown mandated a 25% reduction in urban water use. Why such drastic measures? Just take a look at this data. Between 2014 and 2017, about 60% of California was experiencing what experts called exceptional drought. And nearly the entire state faced drought conditions of some level. After a short recovery, yet another drought hit in 2020, stretching well into 2023. It's a vicious cycle. And while these events vary in intensity, one thing is consistent: California regularly runs dangerously low on water. That's why restrictions are essential to prevent total water collapse during dry years. Oddly enough, while the state was dealing with drought, some regions were hit by severe floods. During these rare but intense storms, hundreds of millions of gallons of rainwater fell in just days. Too much, too fast. The flooding damaged homes, infrastructure, and in some cases took lives. That's the paradox of California. Not enough water when you need it, and too much when you don't. Naturally, this contradiction sparked a big idea. What if California could capture floodwaters and store them for future use? This idea dates back to the 1950s and 60s, when the state first launched the California State Water Project, SWP. It led to the construction of one of the world's largest water infrastructure systems. Key components of the SWP include the San Luis Dam, which created the San Luis Reservoir, capable of storing 792 billion gallons. Another is Lake Oroville, formed by damming the Feather River, with a capacity of 1.1 trillion gallons. Water from these reservoirs is transported through a vast network of pipelines and canals. The centerpiece of this system is the California Aqueduct, a 460-mile water highway that moves water across regions, capable of carrying 98,000 gallons per second. At the southern end of the aqueduct lies the Edmonston Pumping Plant, one of the most powerful water lifting stations on Earth. To give you an idea of its might, it can lift water nearly 2,000 feet, higher than the Eiffel Tower. The SWP is a marvel of engineering, and it served California well for decades. But over the years, demand has outgrown supply. The state's population has more than doubled. Agricultural and industrial needs have ballooned. Meanwhile, climate change has made rainfall patterns even less predictable. That's why the state is building something new, the Sites Reservoir, just west of Maxwell. Why here? The location is ideal. The valley is shaped like a natural basin, surrounded by hills and mountains, minimizing the need for artificial barriers. It's lightly populated, which avoids the social disruptions that dams often cause. And with sparse vegetation, environmental impact is lower. Planning for the reservoir started in 1996. Over the next 18 years, more than $50 million was spent on feasibility studies. The project will require 12 dams, 3 large ones and 9 smaller ones, to contain the water. The tallest of these, the Golden Gate Dam, will rise 285 feet. Not quite a record breaker, but still impressive. For comparison, Lake Oroville's dam stands at 770 feet, making it the tallest in the U.S. The site's reservoir will be enormous. It will stretch 13 miles from north to south and 4 miles across, with a maximum depth of 262 feet. When full, it will store up to 475 billion gallons, ranking it among California's largest reservoirs. But what makes Sites truly unique is its off-stream design. Unlike traditional dams, it won't block a river. Instead, it will divert water from the Sacramento River, but only during times of high flow, and only after environmental and legal obligations are satisfied. During droughts, water from Sites can be released back into the system, providing a much-needed buffer against shortages. According to officials, the stored volume is enough to supply 7.5 million people for an entire year. The water will be moved through existing infrastructure, pumping stations, pipelines, and canals, reducing the need for new construction and minimizing environmental disruption. And there's another advantage. A large portion of the reservoir's water will be reserved for environmental purposes. California's ecosystems have suffered during past droughts, CITES is designed to stabilize river flows, improve wetland conditions, and even help endangered fish species, including the Sacramento salmon. Because the reservoir won't sit on the river itself, salmon migration routes remain unobstructed. That's a major win for conservationists. CITES may also work in conjunction with Shasta Lake to deliver cold water, essential for salmon spawning. Still, it's not all good news. Some environmental groups remain opposed. While CITES won't directly dam a river, it will draw water from Sacramento, and during peak diversion, it could take up to 60% of the river's flow. Critics worry this could endanger not just salmon, but 23 other vulnerable species. Evaporation is another concern. With California's high temperatures, it's estimated that 9.7 billion gallons of water will evaporate from CITES each year, water that will need to be replaced. There's also the issue of emissions. In 2023, the group Friends of the River, backed by the Tell the Damn Truth campaign and funded by outdoor clothing brand Patagonia, released a report stating that the CITES project could emit around 362,000 metric tons of CO2 annually during operation. Much of that comes from methane, released as submerged vegetation breaks down. Despite these concerns, many believe the benefits outweigh the drawbacks. The CITES reservoir is scheduled for construction between 2026 and 2032, and it's a key part of California's water strategy. But it won't be enough on its own. That's why California is also turning to wastewater reuse. As of 2025, the state treats over 224 billion gallons of wastewater each year. Most of this is used in agriculture, which consumes about 80% of California's developed water supply. Reusing water here frees up more clean water for households and industry. The state is also investing in groundwater recharge, injecting treated water into aquifers for future use. In Orange County, one facility alone recharges 98 million gallons per day. Industries are also embracing recycled water for cooling systems, concrete mixing, and even paper production. Why? It's cheaper than raw fresh water and doesn't require extreme purification. So maybe, in the not-so-distant future, California will finally break its cycle of drought and desperation. Not by changing the climate, but by changing the way it stores, uses, and values water. This is the Great Man-Made River, a colossal engineering feat buried beneath the sands of Libya. Dubbed the world's largest irrigation project, the Libyan government even went as far as calling it the eighth wonder of the world. And to many, that wasn't just propaganda. This bold and ambitious project was the dream of Libya's former leader, Muammar Gaddafi. His vision, to turn Libya's arid desert into fertile land as green as the Libyan flag during his regime, a completely green banner representing the Libyan Jamahiriya. But how close did they come to realizing that dream? How was this river built beneath the desert? And what has become of it today? Let's dive into the story of a river without a drop of surface water, a megaproject born out of desperation, vision, and oil money. Let's begin with the geographic reality of Libya. It's a country located in North Africa, with its entire northern edge lining the Mediterranean Sea. But beyond that narrow coastal strip lies a vast and unforgiving landscape, the Sahara Desert. In fact, about 90% of Libya's land area is desert, and half of that is classified as sand desert, a literal sea of sand dunes and rock. Libya's biggest geographical disadvantage is its lack of freshwater resources. There are no permanent rivers or lakes to speak of. Instead, it has wadis, dry riverbeds that occasionally fill with water after rare rainstorms, only to evaporate quickly. These conditions make Libya one of the driest nations on Earth. Most of the country's rainfall is concentrated in a tiny sliver along the coast, which makes up less than 5% of Libya's total area. Even there, average annual rainfall is just around 4 inches. In the interior, rain is practically non-existent, falling in brief, heavy showers at the end of winter and early spring. That's it. Unsurprisingly, most of the population clusters in cities along the coast, where water is at least somewhat available. According to data from 2020, nearly 80% of Libyans lived in urban areas, roughly 5.4 million people out of a total population of 6.8 million. In rural regions, people survive in small pockets, mainly around oases, using traditional irrigation methods for farming. But water access remains a constant struggle. Water scarcity is a well-known crisis in the Middle East and North Africa. The reasons are many: scorching temperatures, high evaporation rates, limited rainfall, and a growing population. Libya is a textbook example. In fact, The World Resources Institute ranks Libya as the sixth most water-stressed country on the planet. Back in the 1960s, Libya began experimenting with desalination, removing salt from seawater to make it drinkable, but it was an expensive and limited effort. Then, in 1969, everything changed. Muammar Gaddafi seized power in a military coup, and soon, his administration began eyeing a much grander solution, the Great Man-Made River Project. Interestingly, Libya's water woes actually predate Gaddafi. During the 1930s, under Italian colonial rule, water shortages were already a major issue. But back then, Libya lacked the money, manpower, and technology to tackle such a challenge. That all changed in the 1950s, when oil exploration began in earnest. In 1953, while drilling for oil in southern Libya, foreign companies made an unexpected discovery. Not only did they strike large oil reserves, they also tapped into massive underground reservoirs of freshwater. It was like hitting the jackpot twice. Further studies revealed that this water came from the Nubian Sandstone Aquifer System, one of the largest fossil aquifers in the world. This ancient groundwater is believed to be between 10,000 and 1 million years old, formed back when the Sahara was a much greener, wetter region. Over millennia, this water became trapped deep underground beneath thick layers of sandstone. The aquifer stretches beneath 4 countries: Libya, Chad, Sudan, and Egypt, covering an astonishing 770,000 square miles. It's estimated to contain around 39 quadrillion gallons of water. That's an almost incomprehensible amount. At first, the Libyan government considered using this water for large-scale desert agriculture, but by the early 1980s, the strategy shifted. A new plan emerged. Instead of trying to farm in the desert, why not transport the water to the densely populated coast? It seemed far more feasible than investing in costly desalination plants that the country couldn't afford to operate or maintain. The coastal aquifers, especially around Tripoli, were also becoming increasingly salty and polluted due to overuse. Meanwhile, a giant reservoir of pristine freshwater lay untouched in the desert interior. The only problem? No one lived near it. The water had to be brought hundreds of miles across harsh, empty terrain. Thus, the Great Man-Made River Project was born. Despite its name, it's not a river at all, but an immense network of underground pipes, aqueducts, reservoirs, and pumping stations designed to move water from the heart of the desert to Libya's cities and farmlands along the Mediterranean coast. But building such a river was no small feat. Construction was divided into multiple phases. The idea was to drill deep wells, some over 1,600 feet into the ground, tap into the aquifer, and then transport the water through a massive system of pipes. By the time it's completed, the network is expected to span over 2,500 miles, with a capacity of more than 1.6 billion gallons per day. In 1984, Gaddafi officially launched the project and laid the foundation stone near the Sarir Aquifer in eastern Libya. The first phase of the project, known as GMR-1, was focused on 2 fields, Tazerbo and Sarir. Hundreds of deep wells were drilled, and the water was pumped through twin pipelines to Ajdabiya, where it was stored in large reservoirs. From there, it was distributed to the coastal cities of Benghazi and Sirte. By 1991, Phase 1 was complete. It consisted of a 990-mile-long double pipeline capable of transporting 528 million gallons of water per day. To build it, engineers installed a staggering 250,000 sections of reinforced concrete pipe, each 13 feet wide and 23 feet long. These were the largest precast concrete pipes ever made at the time, manufactured at 2 giant plants inside Libya using steel-reinforced, pre-stressed concrete. The pipes were placed into 23-foot deep trenches using custom-designed cranes and bulldozers. Each joint was sealed with heavy-duty rubber gaskets and cement grout before being buried. The construction also included massive reservoirs. For instance, one reservoir near Ajdabiya spans over 3,300 feet in diameter and holds more than 6 billion gallons of water, essentially a man-made lake. The numbers are jaw-dropping. Over 5 million tons of cement were used, enough to build 20 Great Pyramids of Giza. The amount of steel wire used in the pipe reinforcement could encircle the Earth 280 times. Just to appreciate the scale, consider this. Libya even built a monument out of one of these pipe segments to showcase the size of a single piece. Following the success of Phase 1, the second major section, GMR-2, was launched in western Libya. Its goal was to supply water to the capital, Tripoli. Phase 2 began delivering water in 1996, pulling from wells in the Jabal Assa area. Additional phases were planned to connect other regions of the country, with the long-term vision of supplying water for agriculture, domestic use, and eventually industry. Water from the Great Man-Made River was intended to revolutionize farming in Libya. In theory, it would irrigate thousands of acres of land, boost food security, and reduce reliance on imports. And for a time, it seemed to be working. But the project wasn't without criticism. Many scientists warned that fossil water is a non-renewable resource. Once it's used up, it's gone forever. The Nubian aquifer is not actively replenished, especially not in a region where rainfall is so rare. Some also questioned the environmental and geopolitical implications of extracting water shared by multiple countries. Then came the civil war. After Gaddafi's fall in 2011, Libya plunged into political chaos. Maintenance of the great man-made river became difficult. Many of the pumping stations and pipelines were damaged during the conflict. In recent years, armed groups have even used water flow as a bargaining chip, cutting supply to cities like Tripoli for political leverage. What was once a national symbol of pride is now struggling to stay functional. Still, the great man-made river remains a powerful example of human ingenuity, a testament to what's possible even in one of the harshest environments on Earth. Whether it will continue to provide water to future generations, however, depends on Libya's stability, resources, and commitment to managing this fragile legacy. So, did they manage to turn the desert green? For a moment in history, they came close, but the river, like the nation that built it, now stands at a crossroads. Here are 9 countries that border the Baltic Sea, but recently, global attention has focused on just 2 of them, Germany and Denmark. Why? Because nestled between these 2 nations is the site of one of the most ambitious infrastructure projects in European history. If you sail through this area, you'll notice something unusual. Artificial land formations, newly carved out channels leading into the sea, and at times, as many as 70 ships scattered across the horizon. Not exactly your average maritime traffic. These vessels weren't there for sightseeing. They were part of a massive operation that involved digging up more than 76 million cubic feet of soil and rock from the seabed. So what's going on here? It's all part of the Fehmarnbelt Fixed Link, a 10 billion euros megaproject that's not just rewriting engineering records, but also transforming how Europe connects. Off the coast of Germany and Denmark, 2 entirely new harbors have been constructed, each capable of handling nearly 100,000 tons of raw materials per week. An enormous production plant, covering roughly 11 million square feet, has also sprung up. All of this is to make way for a tunnel. But not just any tunnel. This project is building what will soon be the world's longest immersed combined road and rail tunnel, a direct connection between the German island of Fehmarn and Denmark's Lolland Island. Up until now, crossing between the 2 meant relying on a ferry, a process that involved queuing up, boarding, and sitting through a 45-minute ride across the strait. And that's on a good day. Storms, strong winds, or fog could easily delay service by hours, so the idea of a permanent, fixed link has been on the drawing board for decades, since at least the 1990s. Initially, the concept was to construct a 12-mile cable-stayed bridge with a 4-lane highway and 2 electrified railway tracks. The design was dramatic, featuring 4 giant pylons, each nearly 920 feet tall, and 3 central spans, each stretching 2,375 feet. If built, it would have set world records for the longest spans on a combined road-rail bridge. Construction was supposed to begin with the goal of opening in 2018. The Danish company Femern AS was awarded the contract to develop the project. But then came a major pivot. In 2010, after extensive studies and engineering assessments, Femern AOS concluded that a tunnel would be the better option. The reason? Fewer technical risks and a more predictable construction process. The seabed's geology, with its challenging mix of soft clay and hard limestone, made the bridge option far more complex and risky. Plus, the cost difference between the bridge and the tunnel was surprisingly small, 5.2 billion versus 5.5 billion euros. Construction time wasn't drastically different either, 5.9 years for the bridge versus 6.5 years for the tunnel. So the plan shifted. The tunnel became the official design. The tunnel, once complete, will stretch 11 miles, about 18 kilometers, and carry both road and rail traffic. It will consist of 2 double-lane motorways, 2 electrified railway tracks, and a service tunnel in the center. To support such a massive structure, construction had to start not just with digging, but with building the facilities required to produce and transport the enormous materials needed. That's where the gigantic manufacturing plant comes in. Built near the Danish town of Rødbyhavn on Lolland, this facility is the largest of its kind in the world. Inside, 6 production lines churn out the precast concrete elements that will form the tunnel. Each segment is a monster in its own right, 712 feet long, 131 feet wide, and 33 feet high, and they weigh a staggering 73,500 tons. just shy of a fully loaded cruise ship. In total, 79 of these standard tunnel segments will be needed. On top of that, special segments will be created to house technical equipment and emergency access systems. And since transporting these massive tunnel elements from distant locations would be logistically impossible and prohibitively expensive, the production plant was strategically built just a few miles from the actual tunnel site. Even the harbors were purpose-built to receive raw materials like gravel, sand, cement, and steel, capable of handling tens of thousands of tons weekly. The German side at Puttgarden also got its own smaller port to support the construction effort. By 2024, dredging operations were in full swing. Ships of every kind filled the Fehmarnbelt: cutter suction dredgers, trailing suction hopper dredgers, and specialized stone clearance vessels. Their mission was to dig an 11-mile trench between Fehmarn and Lolland. The trench measured up to 164 feet wide and almost 50 feet deep. The seabed's natural conditions were tough, ranging from soft clay to hard limestone, but the specialized fleet handled it all. Rather than dumping the excavated material, engineers decided to reuse it. The soil and rock were transported to a designated area off Rodbyhaven to create 741 acres of new land. This reclaimed land will eventually become a mix of natural habitat and recreational zones, complete with beaches, parks, and trails. With the trench now complete and reinforced with gravel, the next monumental step begins: laying down the tunnel sections. Entrances to the tunnel have already been constructed on both Lolland and Fehmarn. These massive portals serve as gateways for the submerged structure that will rest beneath the sea. Transporting and positioning each tunnel section is no small task. Each segment will be attached to floating pontoons, then guided into place by tugboats. This delicate process, known as immersion, won't be done remotely. It will be operated from a control room located on one of the pontoons. A team of 22 people will oversee the process, using high-precision underwater cameras and positioning systems to guide the section into the trench with an accuracy margin of just half an inch. Once each section is perfectly placed, large rubber gaskets, engineered to last 120 years, will be installed between them to ensure watertight seals. Then, layers of soil will be placed back over the entire tunnel, burying it beneath the seabed. In the end, this will be a tunnel that is both underwater and underground. But if installing just one tunnel segment takes up to 40 hours, how long will the whole project take to complete? That's the million-euro question. When plans were first floated in 2012, the goal was to open the tunnel by 2021. A few years later, the date was pushed to 2024, then 2028. Finally, in 2020, the official opening date was set for 2029. Many are eagerly awaiting that year because the benefits of this tunnel will be enormous. Travel time will be slashed dramatically. What is currently a 45-minute ferry ride will become a 10-minute drive through a modern tunnel. Even better, high-speed trains will cross the same route in just 7 minutes, reaching speeds of up to 124 miles per hour. Zoom out on the map, and the bigger picture becomes clear. The tunnel isn't just about connecting Fehmarn and Lolland. It's about reshaping transportation across Northern Europe. Once completed, it will create a direct link between Scandinavia and Central Europe. Freight trucks, passenger vehicles, and trains will be able to travel seamlessly from Copenhagen all the way to Hamburg, reducing congestion, cutting emissions, and boosting economic ties. It will also strengthen the Trans-European Transport Network, TEN-T, the EU's plan for integrating infrastructure across member states. In short, the Fehmarnbelt Tunnel is more than a regional project. It's a continental game-changer, and it's breaking records along the way. When finished, it will hold the title for the world's longest immersed tunnel, the longest combined road and rail tunnel, the longest underwater road tunnel, and the second deepest underwater concrete tunnel ever built. It's not just a feat of engineering, it's a symbol of ambition, collaboration, and the future of European connectivity. From blueprint to reality, the Fehmarnbelt Fixed Link is a marvel in motion. And as the countdown to 2029 continues, it's already shaping up to be one of the defining infrastructure projects of our era.